Again, my name is David Deal, and I work for Intergraph. Okay, I won't say that we're sponsoring this session. Mike Conaway of Plant Design Solutions is basically ramrodding this affair, and we were offering our space. Welcome to our office. We've been here for like 2 months now, I guess. This is a brand new training room, and we still got some hardware to settle down, but I think we're going to have a pretty good show with what we have here today. And again, we're not just endorsing SPED, but actually the Houston chapter. We want to see this get developed. What Mike wants us to do today is review a little bit about CESAR 2. SPED, Society of Piping Engineers and Designers. Okay? My guess is that almost everyone here is on the designer side. That's my guess. I'm not going to ask for hands. But just to push it more towards the engineering side, I want to take a few minutes, maybe 15, 20 minutes to review the CESAR 2 package that we offer here. That's basically what I do for a living, is train people and support people in using CESAR 2. So I have a very brief PowerPoint here, and eventually we're going to be running this model here through analysis. So the workflow is that the designer will develop the drawings, and they'll have a critical line list, and this critical line list will identify which layouts have to be analyzed for safety or for load on equipment. And then those drawings go over the wall to the engineering side, and they use a program like CESAR 2. So this is that CESAR 2 side. Again, I have a very short PowerPoint to work with here. Just a quick look at I'm saying a commercial pipe stress program. Just about everybody uses commercial software for this these days. It's just too difficult for a company to pay for the staff to develop in-house software for this. So there's a very limited number of packages around the world that can do this type of analysis, and CESAR 2 is one of them. We'll take a very brief look at the background and then the application, and my focus is going to be on a quick example, just to give you an idea of what it looks like. I'll say CESAR 2 is the most popular pipe stress program in the world. It's been around for a long time. It came out in 1984. The first machine that it ran on officially was the IBM PC XT. If you're around in 1984, that was a great machine. 64K of RAM, screamer. 20 megabyte hard drive. And that same architecture that was built back then to run CESAR 2 is still used today in the structure of our files and like. And it was born here in Houston. Tony Paulin is the original author. He and Rex Evans developed COAID into the company that was the owner of CESAR 2 until, I guess, 3 years ago when Intergraph purchased us and added us to their suite of software. It's a system analysis tool. I like to say it as like think of the piping system as across the street, and you're evaluating that piping system, not up close. We're not talking about finite element analysis per se, but a general view of that piping system to ensure that it is rugged enough for its application and it is safe. That's the bottom line in all this analysis, is safe operation of piping systems. A lot of these piping systems are carrying high energy systems, and any sudden release of that energy could be cataclysmic. I think we've all seen pictures of some of these failures that have happened in these piping systems. So what we're doing is we're evaluating the system. It's a system tool, not a local tool. And basically the only equation that you got to remember out of this is F equals Kx. Load equals stiffness times deflection. That's pretty much the whole ball game in CESAR 2. We represent the pipe in your model as beam elements, beams and bendings, like little slender rods, okay, with elbows and stuff like that, and T's where they join. So the stiffness, or the K part of that, is from the pipe itself. The F is the load on the pipe. It could be thermal strain, it could be dead weight, it could be relief valve discharge, seismic G load, any type of a load like that. And then you take that equation, big stiffness equation, big load vector, and you solve for the final displacement. So again, this piping system is across the street, and it's in operation, so it moves to a certain point in space. It's in equilibrium, so once you know where it is in space, every end of every piece of pipe, you can calculate local forces and moments, and from that you can then calculate the stresses in that system. Now, the stresses we calculate are code-defined stresses. B31.3 is typical around here. Process piping code. B31.1 is the power piping code. CESUR 2 has like 35 different piping codes in it around the world, and basically we just apply those rules and how to calculate stress in their terms, and then we compare those calculated stress to the defined limits in stress for our model, okay? That's what we do. Basically, we just make sure that the expansion stresses that we calculate are less than a code-defined allowable stress, and that the sustained stress, the collapse loads that cause stress, are also less than the hot allowable stress. That's basically 31.3 stress calculations. That's what CESUR 2 does. Oh, it does more, but let's just talk about that. Now, the engineer who's doing the analysis basically has three goals in mind. Basically, calculate those code-defined stresses and evaluate them. In many cases, though, the load on the equipment is going to be the tail wagging the dog, if you will. It's the equipment that is more sensitive. When you get close to a pump, you might only be using only 5 or 10% of the allowable stress in the pipe in order to get the load on the pump low enough. So this is where a lot of the work of the engineer goes into making sure there's enough flexibility in the piping system so they don't overload equipment. And finally, you have to know the final position of the pipe as well to avoid clash or sliding off of supports and things like that. So basic structural analysis with code position is also part of the game too. Now, most of the people who use CESUR 2 are in new design. In fact, it's, I guess, unfortunate that most of the people that run CESUR 2 now are sitting in an office and they never see the piping system that they've designed, which gets them too far away from the real practical application of the software. It's just a computer game to a lot of people. But it is also used in existing installations. And this would tie in then with things like what Mike will talk about later with field pipe, where you can get as-builts and bring them into, let's say, CADWorks, and then from CADWorks on the design side over to CESUR 2 for the analysis of the as-built systems. So it's also used for existing systems. We're going to run a quick example here today, and I got to watch my time. Here's a piping system, all right? We have, this is the analog, okay? A drawing, a picture, an idea. And what you're going to do is you take this analog and you create a digital model of it, and that's your input to CESUR 2. And this is what the engineer will do, convert this picture into digital information that then the program takes that digital information and runs the analysis. So what's kind of interesting when you have classes here is that we'll have, well, last seminar we had 30 people in this room, and we'll get 5 or 6 different answers. And I try to impress on these people that, look, everyone has their own idea of how to interpret this analog in creating their digital model. And you have to have enough confidence that you're doing a good job so when you go back to your office and you're the only guy running that single model, that you've got good confidence that it's going to be the proper model. It's very easy to get bad numbers to go through this program, all right? So it's up to the engineer to assure themselves that this model is correct. Well, here's our model. We have here the basic layout shown with the dimensions. Here's a coordinate system. We have boundary conditions. Our analysis will go from these 2 anchors down here at the bottom to this anchor at the top. This anchor at the top has some thermal growth associated with it, so I'm going to assume there's some vessel over here. And when the vessel gets hot, it grows vertically and radially, and it imposes that deflection on this boundary condition up here. Our loads are defined based on temperature and pressure and dead weight of the pipe and dead weight of insulation and dead weight of fluid. The stress criteria, we're going to use B31.3, and that piping code has a material database with it that says, okay, A1 is 6th grade B, the cold allowable stress is 20 KSI or something like that. And the hot allowable stress, when this pipe is at 625 degrees Fahrenheit, there's another allowable stress at that point. So that's some of the data that comes with the software as well. Stress criteria, and finally the node numbers. We have to, again, digitize this for the machine. And what do? We basically run this stick model. This is the undressed version of CESUR 2. This is what you're actually running as far as analysis. We don't know all about this piping system. We know about these individual points in the piping system. So the user will define these node numbers throughout and use that then to create the model. So I'm going to have an element from 10 to 20. It's going to be 10-inch pipe, 1 foot 4 inches long in the negative Z direction of that temperature and pressure. Then 20 to 30 is the valve, 30 to 40 is the pipe to the elbow, and so on. So we just put these node numbers at the end of every element, and that's our model. That's what we're going to analyze, okay? So let me start up Caesar 2 now. And I'm going to say it's a new job. I'm going to call it SPED. And of course, we've got a lot of different units available to us. We're going to use the old US customary units here. And here I'm now in the input processor. Now recall that first piece of pipe, it was from 10 to 20, 1 foot 4 in the minus Z direction with these properties on it. Well, I can define that here. 10 to 20, I'm going in the Z direction, minus 1 foot 4. My pipe size is 10 inch. It converts it to the actual. It is standard wall. I think I had a corrosion on here. Yeah, 1/8 inch corrosion. Pipe density will come from the material. Fluid density, it's some hydrocarbon at 0.72 specific gravity. Temperature 1, I think, was 625. 625 and pressure is 250, so temperature 625. And this is where a lot of the load's going to come from, the thermal strain in this pipe. 100 feet of pipe at 625 degrees Fahrenheit is going to grow about 5 inches. Okay, so that has to be somewhere. And that's what this program does, is it calculates the response to the thermal strain. And I forgot what I said for the pressure, 250? Yeah, 250. Now you're going to say, is he going to type all these numbers in every screen? No, a lot of these numbers just carry forward to the next screen for you. You don't have to type all these in again and again. At node 10, we have an anchor. That's our boundary condition there. And our material was A106 grade B. That's in our material spec, it's called 106. We're defaulting to B31.3, and there's our cold allowable stress and our hot allowable stress at 625 degrees Fahrenheit. We have some insulation. I think it's 2.5 inches of calcium silicate. Okay, and that's my first piece of pipe. Okay, I'll go on to my next piece of pipe now. Here, let's put our node numbers on here. There's 10 and 20. I'll continue on to the next pipe, 20 to 30. That's that gate valve. And it's a listed component. There's a given length for that. Do I have to know those lengths? Well, no, I'm just going to, in Caesar 2, say it is a 300-pound flange gate valve. Okay? So I'll go to the valve flange database, and gate, flange, 300 pound. Okay? That's my next element. Now I go on to the elbow, and that's 2 foot 8.5 in the Z minus 2 foot 8.5. I have a bend out there, and I go on to 50. And again, I'm not typing these numbers again. It's very convenient this way. Now I'm going to go in the negative X direction to a reducer. The reducer is 3 foot 6 away. So now X minus 3 foot 6. Now I put in my reducer. That is 8 inches in the negative X. I'll call out the reducer here. The exiting diameter will be 12 inch, and that will be standard wall. And now I go to my intersection. I have a T, a welding T in here, and I'm just going to the center of the T. And this is one of the, I guess, the big differences between a pipe stress program and what most designers work with in CADWorks or SmartPlan or Aviva, is that as a designer, you're working with components, a elbow or a T. In Caesar 2, we're going based on the skeleton of this thing. I'm going to the center of the T. I'm going to some point that you guys wouldn't worry about. I need to know that center point because that's where I'm going to calculate my stress, the center of this T. And so that's another 10 inches down the pipe here. So I'll continue on to the T. That's at node 70. It's in the x direction minus 10 inches. And I have to tell the machine that it is a T because we're going to have it's a weaker component than straight pipe, so we will increase the calculated stress with, I think, a term called the stress intensification factor. Well, there I am at node 70, and now if you look at this drawing, you say, well, hold it. That's symmetric. Can I duplicate that? And of course, I'm going to say, yeah. I'll come in here and select that entire model, and I'm going to duplicate it. I'm going to mirror YZ, so when I'm going negative X, it'll then be positive X. And I chose my node numbers so that if I add 70 to all these numbers, it'll give me the other half of the system. And you say, oh boy, that looks awful. Well, it's just one bad node number over here. I'm going to come to this piece of pipe. It's not supposed to be 130 to 140. It's supposed to be 130 back to 70. So I'm just going to say 70 right here. And then we're buttoned up. And now I'm going to go up in the Y direction to node 130. If you remember, I'm sorry, yeah, 140. If you remember those node numbers. That's 23 feet up. And again, now we're in 12-inch pipe. And we're going to say put a bend up there. And finally, my last run of pipe is to 150. I'm going in the Z direction minus 6'6". And I put my boundary condition up there at well, it's not an anchor, sorry. It is instead a set of displacements and rotations. And that's the model for that vessel that's up there. That's my entire model. Now, what you would normally do then is make sure it's a good model. You might do something like this, show the different pipe sizes. I've got 10-inch and 12-inch pipe. That looks right. I can look at my wall thicknesses. Everybody's at 625 degrees Fahrenheit. It's all 250 psi. That looks pretty good. And of course, you should check coordinates, but because of time constraints here, I'm just going to say, well, I'm assuming this model is correct. So I'm going to do error check on it. And the program is saying I do have an error in my model. It's basically inconsistency. It says, well, it says an error on element 130 to 70. You have an invalid intersection node number. So you say, well, what's that all about? Well, what you can do is tell the machine to go zoom to that selection. I'll select this one, and I'll zoom to it. And it's complaining about that run of pipe in my system. Now, what about that line of data? It's right here. And it's 130 to 70. It says invalid intersection specification. Well, here it is. Well, who put a SIF at node 140? Well, that was my duplication. I did that one. And you remember before I changed that to node 70, that used to be 140. So I'll clear the error by just getting rid of that. And I'll do the error check again. And no errors. Now I've got two warnings. It says that I did not specify the slope of this reducer. Well, I don't know what it is, and in this piping code, I don't have to know what it is. So it's just a warning. There's no error involved with that reducer and the other one. So that's what those messages are talking about. But here's my center of gravity. I've got about 6,000 pound system here. And now I want to do analysis on this. So I'm going to have the program suggest what load cases should be analyzed. And we have this selection here. We'll do an operating load set. We have the dead weight of the pipe and insulation and fluid, that anchor displacement up here at node 150, the temperature and the pressure in the line. That's an operating case. We'll also do an installed case, find the installed position. And unique to piping codes, they look at the change between the installed and operating. They call that the expansion stress range. So those are where we're going to run. So I'm going to click the running man here, and we run the analysis. And I'm at the output menu now. Now, right away, there's something wrong here. It's overstressed. What we can do, though, is take a quick look at the plot of the system to make sure it's reacting properly. There's our layout. I'm going to displace it, and we see here that this is a representation of the system in operation. That's that displacement. It's not to scale, but there's that displacement we had up at the top, with the two anchors down at the bottom. And it looks like it's doing the right thing. I'm seeing the top end is growing up, the bottom's growing down a little bit, and I'm opening up the the loop at the bottom. So it's believable. I'm now going to look at the numbers, displacements of the operating load case. Again, this is an operation. Node 10 is our anchor. That doesn't move at all. Node 80 is the other anchor at the bottom. That doesn't move. Node 150, there's that ½ inch, and there's that 1/8 of an inch I typed in. And these are the deflections of every other node that's in this model. Okay? That's the root solution. I have the same solution for the sustained case. Well, one report that a lot of people are interested in is the restraint report. I mentioned earlier that the designer will throw his drawing over the wall to the stress engineer. Well, the stress engineer in bigger organizations will throw these numbers over the wall to the support engineer to build and size the supports. So they will want to know these numbers. Although, before I say that, let me say, if it's overstressed, you're not going to show these numbers to anybody because it has to be changed, okay? So there's some work to be done here. But this is the restraint report. Here's the loads on the anchors at 10 and 80, those two anchors at the bottom, and then that nozzle up at the top. These are very, very large numbers. So nobody's going to build this system. In terms of stress, I'll just talk about this one. This is the expansion stress range case. This is the case that we run in order to assure ourselves that the system will not fail by fatigue over the life of the installation. And right now, since it's in red, I'm going to say we can't build it. But here's the stress report, and basically, I'm going to focus my attention on the code stress column and the allowable stress column, or maybe just this ratio column. I'm 8% over the allowable stress, okay, at the two anchors at the bottom. So to make this a happy ending, I'm going to go fix this model so it does pass and it can be built. So I'm going to go back to my input processor. And this is where the engineering comes into play. I have a very, very large bending moment about the y-axis at these two anchors, and that's caused by the thermal strain of this leg's growth. I also have a very, very large bending moment about the x-axis on these two anchors down here, and that's caused by the thermal strain of this run of pipe. For me to reduce the effects of strain in this direction and this direction as they apply back to those two anchors, I want to increase flexibility in this run. Now, do I want to go back to the designer and say, hey, could you move that vessel over for me? Okay, well, now you know the answer to that. So instead, I'm going to say, well, I've got 6 feet up here. Maybe I can steal some of that length and put it down here. Maybe. I'm not a designer, but I'm going to do that here on my model. I'm going to say, well, that's 6 foot long. I'm going to make it 3 foot long instead, and I'm going to put that 3 feet down here. That's 2 feet. I'll make it 5 feet, and the same on this end. Okay, so now I still got everything synced up and flanged up properly. I'll just click the running man, run the analysis. And this will be my happy ending. Look, no overstress. I am now below, I'm not saying we can build it yet, but on stress alone, we used to be, what, 8% over, now we're 10% below the allowable stress. That's the maximum stress in the system. This is still the maximum stress here. Again, code-defined stress, allowable stress, ratio. So that's our happy ending for the Caesar 2 analysis.
Will it go back in and allow you to, will it change the analog drawing?
Will it change the what?
Analog.
The autolog?
The analog drawing.
Analog. Oh, okay. It changed the view. Now, yeah, it changed it on this one too. So that's the new layout. Now, what we can do is, one of the major reasons why I'm talking about Caesar 2 here right now is because certainly with our CADWorks package, I can push this back to the CAD application and it will have this drawing. Or I could give it back to the designer and he can overlay this drawing on top of the original and approve the changes that I suggest. So, but Caesar 2 will do the analysis, but it doesn't do anything more with it. We're basically at the end of the road here with Caesar 2. But I can do the good handshake with the CAD side on the model itself.